Hello, chemists. This is Ms. Placino, and you're watching lesson 5.3 on balancing equations. In today's lesson, we're going to discuss how to balance chemical equations in terms of mass. Goals for today's lesson: identify indications that a chemical reaction is taking place. And the big one for today is being able to balance simple chemical equations with whole number coefficients. Let's get started. So let's start with signs that a chemical reaction is occurring. And another name for a chemical reaction is simply a chemical change. There are some signs that we can look for that usually indicate that a chemical change is taking place and not just a physical one. So let's see if you can get them based on the pictures. What do you think I'm trying to show here? Yeah, this is the evolution of heat and or light. This is often a sign of a chemical reaction. Think about lighting a piece of paper on fire. That is a chemical change, and heat and light are both produced. What about here? Yeah, this is a change in color. Sometimes the color change can be associated with a chemical change. In this case, we have an indicator. It's called phenolphthalein. We'll be revisiting that much further down the road. But it is changing as changing colors, as a chemical change takes place. How about here? Yeah, this is production of a gas. So in this case, we're producing carbon dioxide bubbles from a solid, and that is an indication that a chemical change has taken place. Don't confuse that with something like boiling. We've got a pot of water on the stove, like little bubbles form at the bottom and move up towards the top and ultimately escape as a gas. That is not a sign of a chemical change. Usually we need something being added to water in this case and producing a gas from there. And last but not least, this looks like another color change, but if you were able to just sit and let this settle, you would see that this is actually a yellow solid being produced. Yeah, the production of a precipitate is often a sign of a chemical change as well. All right, so once you've identified a change as being a chemical in nature, or just simply a chemical reaction, we can go ahead and try to balance that equation. Let's talk a little bit more about chemical equations. We'll take a really simple one. 2H2 parentheses G plus O2 parentheses G, arrow pointing to the right, 2H2O parentheses L. What does this mean? There's a ton of information packed into a chemical equation. Those numbers that come in front of the H2 and the H2O are called coefficients. And ultimately, that's what we're going to be using to balance an equation. These things in parentheses, L over here and the two G's, those are the phase of matter. L stands for liquid, G, gas, S is of course a solid. You'll also see a Q for aqueous. We'll talk more about that in a minute. Everything that is on the left side of the reaction arrow are collectively referred to as reactants. These are just the materials or the substances that enter a reaction. To the right of the reaction arrow, we have the products, and this is going to be the material or materials that exit a reaction, so after the chemical change takes place. And all chemical equations are set up this way. Reactants on the left, products on the right. We use coefficients to balance. You may or may not have these phases of matter included. So just to revisit this idea of aqueous. Aqueous means dissolved in water to form a solution, and a lot of the chemicals that we work with in the lab do tend to be aqueous in nature. To make an aqueous solution, and I'm sure you've done this before, you take a solid, you add it to some water, and you just stir it until it's homogeneous. This happens to be a solution of copper 2 sulfate pentahydrate, but it's the same idea as salt water or sugar water. Solid gets dissolved, stirred up, and you've got a homogeneous mixture. When we go to balance chemical equations for mass, we're really applying the law of conservation of matter. Basically, that tells us that matter cannot be created or destroyed. It can only change forms. Really, what the implication is for us with balancing is that the number and type of atom on the reactant side has to match the number and types of atoms on the product side. We can't create or destroy anything, but we can change its forms. You might want to make a note of this somewhere. Mass, energy, and charge are all conserved in chemical reactions. We're going to focus on mass during this unit, and we'll look at like energy and charge in future units, but all of them have to be conserved over the course of a chemical reaction. Let's try to balance our first equation. So there isn't any real shortcut. We could balance by inspection, which is just kind of a fancy word for guess and check. It turns out that there are smart guesses and there are kind of crazy guesses, and we're going to work through this together. So the first thing you want to do is just kind of evaluate and see what you have as reactants and products. So on the reactant side, I have one Sb, antimony atom, and an O2 molecule, okay? On the product side, I have 4 Sbs and 6 oxygens. I balance using coefficients. Remember, those are the numbers that come in front of the elements or compounds. You can't just go through and like cross that out and turn that into a 2 and be like, there, it's balanced. That is, of course, not how it works. So we've gone through and we've counted the number of atoms of each element on both sides of the equation. Now we're going to try to balance the atoms using coefficients. Again, no changing the chemical formulas. That actually changes the reaction and is not a valid way to balance. Let's say we can do this. I've got 4 antimonies on the product side. How can I get there to be 4 antimonies or Sb atoms on the reactant side? Yeah, let's just put a coefficient of 4 there. 4 antimonies, 4 antimonies. Nice. Let's go ahead and look at oxygen. I've got 6 oxygen atoms over on the product side. I've got 2 on the reactants. Well, if I have 3 molecules of O2, 3 times 2 gives me 6 of oxygens now on the reactant side as well. And you can put the 1 there if you want to. More often than not, it's just left out. If there is no coefficient, it's assumed that it's a coefficient of 1. Lots of students skip over this last step, but it's really worth taking the extra 10 seconds and just double checking. 4 SBs, great. 2 times 3, 6 oxygens, 6 oxygens, done. As the reactions become a little bit more complicated, it's going to become more and more important that you check your work to make sure you didn't do something careless. Let's look at a handful of practice problems. All right, so I'm over on the practice problem page, and it probably looks a little overwhelming with 40 different equations to balance. You might not need to do all 40 of them, but I can guarantee you, you're going to need to do more than like the handful that we're going to look at to start getting competent, confident, and just plain old quicker with this stuff. So I want to look at, let's look at reactions 2, 4, and 2, 3, and 4. We'll do them and see what we come up with. So if you think you've got it, feel free to pause the video, work these out on your own, and then check in. Or if you're feeling a little shaky, no problem. Let's start walking through them together. So we'll start with question number 2. I've got boron mononitride, fluorine on the reactant side, boron trifluoride, fluoride, nitrogen on the product side. Okay, I see a nitrogen, 2 nitrogens. I see 2 fluorines, 3 fluorines. I already got 1 boron. So I shouldn't start with borons. They're already kind of balanced. There's already 1 on each side, so that's not a smart one to start with. For no reason in particular, I'm going to take a look at nitrogen. 1 over there, 2 on the product side. If I put a coefficient of 2 in front of the Bn, I've balanced up for nitrogens. Now I've unbalanced, if you will, my borons. 2 borons on the reactant side. If I want to get 2 borons on the product side, I'll just stick a coefficient of 2 in front of boron trifluoride. Let's see what's happened to the fluorines as a result. 2 times 3, that's 6 fluorines. If I put a coefficient of 3 in front of F2 on the reactant side, that will balance up. For the sake of completion, I'm just going to put a 1 there so that we know we didn't like leave it blank accidentally and that we actually finished the problem. These blanks all the way over to the right, we're going to leave those alone for the time being. We will need them for the next lesson. I'm going to skip number 3 and come back to it. That's one of the more challenging ones. And I'll take a look at question number 4. All right, I've got hydrogen, phosphorus, and oxygen to play around with. This is kind of a tough one because hydrogen shows up in every single term. So maybe I'll wait and do that one a little bit later. It's kind of a tip. Same thing with oxygen. It also shows up in every substance in the equation. Maybe I'll hold off on that one too. I guess that leaves me with phosphorus by process of elimination. 2 phosphoruses over on the product side. Let's put a coefficient of 2 in front of H3PO4. That gives me 6 hydrogens. Okay, let's see, I've got 4. Oh, plus 2, that equals 6. All right, so far so good. Let's see if oxygen happens to be balanced as well. 2 times 4, 8 oxygens. 7 oxygen plus 1 oxygen, 8 oxygens. Balanced. All right, question number 3 is a tough one. We are trying to balance what's called a double replacement reaction, and we've got a lot of elements to keep track of. Here is a suggestion. If you look, we've got SO4, the sulfate ion, and it shows up as SO4 on both sides of the equation. Same thing with the hydroxide ion, OH. My suggestion would be, instead of trying to treat sulfate as a sulfur and 4 oxygens, treat it as a single unit. Treat it as a sulfate. Same deal with the hydroxide. Don't treat it as oxygen and hydrogen. Treat it as a group. That might make balancing a little bit easier for you. I'm going to start with iron. I've got 2 iron atoms on the reactant side. I have only 1 on the products. I'm going to put a coefficient of 2 in front of FeOH3, iron 3 hydroxide, to balance the irons. Well, I probably did something to my hydroxides. So I've got 3 in the formula, 3 times 2, 6 iron 3 hydroxides. Put a coefficient of 6 in front of the potassium hydroxide to balance up hydroxide. Again, I don't want to think about it as oxygen and hydrogen. I'm going to combine it into a single group. All right, now I've got 6 potassiums on the reactant side. I come over to the products, I have just 2 potassium. What coefficient should I put in front of potassium sulfate? Hopefully you're thinking 3, because 3 times 2 gives me 6. I'm balanced for potassium. And finally, we'll check sulfates. Hopefully they're balanced. I have 3 sulfates on the product side, 3 sulfates on the reactant side. So that just needs a coefficient of 1. Balancing takes a little while to get good at. It's this constant kind of back and forth between reactant side and product side. Once you balance for one element, there's a good chance you've unbalanced something else, whether it's an element or a polyatomic ion, and you just kind of bounce back and forth. Our coefficients, for the most part, are going to be very reasonable. What I mean by that is often like 10 or lower. In most cases, we're talking about 4 and lower. So if all of a sudden, in most cases, you end up with like, man, I got a coefficient of 37, maybe stop what you're doing and double check your work. Make sure that it makes sense. Usually we'll have pretty small coefficients, 4 to 6, getting as big as most of them will. There are some exceptions, and you'll know when you get there. All right, as always, practice, practice, practice. Get more confident, get comfortable with this. We will be doing really a lot of balancing moving forward. All right, that wraps it up for today. Thank you for tuning in, and I hope you found this helpful.